Welcome to the second video for tactics movement. For tactics movement, there's a few more things we need to cover. So we've got the map created. Now we actually need to do pathfinding for player movement, pathfinding for AI movement, and then we have to create the movement system. So there's really three more parts, not counting the turn manager between NPCs and PCs. So for this video, I'm going to cover the player aspect of it. So first I'm going to cover player movement, specifically the pathfinding for player movement. So for pathfinding for player movement, we're going to use graph theory, and the algorithm we're going to use from graph theory is called breadth first search. So breadth first search, or BFS, does a kind of localized search, and then we're going to trim it so that it only goes up to a player's movement for a player. Slow characters have movement between 3 to 5 tiles. Fast characters can be between 5 and 7 tiles. I'm going to use a movement of 5, which is kind of in the middle, considering I have a 12 by 12 grid. So when we cover BFS, I'll go through the details of it. But before we get that far, we need to set up the tiles, and we need to set up the player script. And I'm also going to add a capsule for the player. In fact, let's go ahead and put the player in right now. So to put the player in, we just create a 3D capsule. And let's go ahead and put it into the 000 for now. Now, I want to quickly move this on top of a tile. So let's go to let's click on a tile. So tile 5 of the first row, and let's drag until it's parented to tile 5, then reset. Now that puts the capsule directly inside the tile. And you notice that the capsule is the same size as the tile. It's taller, but it's the same width and height, or same width and length. I actually want it smaller, so I'm going to do 0.9, 0.9, 0.9. So it's a little bit smaller. We could even go a little bit smaller than that if we want to. Next, I want the capsule to be sitting on top of the tile. So we at least want to go Y1. Now notice in Y1, it is still inside. So we need to add about half of the width of the capsule. So 1.4. 1.4 looks to be about right. It's touching. So I would say that is sitting on top of. Now that it's sitting on top of, we can unparent it so it's separate. We don't really actually want it parented. And if we zoom out, it is now centered and sitting on top of a tile. So from here, let's go ahead and call this player. Let's go ahead and give it a player tag, just because that's one of the players. We could give it a separate name. It doesn't have to have the name player, but I wanted to make it very obvious for this example. It's going to need a material. So let's go ahead and make a material for the player. We'll call it player mat. Just drag the player mat onto the player. Let us go ahead and give some color to that. I don't have a texture. So let us make the player, let's just make him blue, just so we can quickly find him. So we now have a player. He's blue. He needs a script. So let's go ahead and create a script called player move. And we'll just drag that script. It's not letting me do it yet. Let me go ahead and reload this. And now it's been compiled. And so now we have the beginnings of the player. So we can go over to the script now and just take a quick look at the script once I actually click on it. Now, the way the player moves and the way the NPCs are going to move is actually identical. The only difference between them is in the algorithm used to determine how they're going to move. So that means all the movement code and even a lot of the selection code for determining what tiles are traversable is going to be shared. So by sharing, that means we actually want to derive the player move and the NPC move, which I haven't created yet, but I want to derive them from a base class. And all the code that's going to go to manipulating the movement, which I'm going to call tactics move. Tactics move is going to define all of the movement code. Then player move, instead of inheriting from mono behavior, is actually going to inherit from tactics move. So any code that we put in here that's, well, any code we put in here that's protected or private is going to then be used in player move and NPC move. So this is a good way of sharing the code. I don't need start and update and tactics move because it's going to be in the top class, but I do want an init function. And there's going to be a lot more code. In fact, most of the code for movement and path selection is going to come into tactics move, and we're just going to use it inside the player move class. So in start, we'll just call init, and then we're going to have to add a bunch of code here. For example, when it's the player's turn, the player is going to be able to select a tile that's in their movement range, and then they're going to move to that tile. So before we get that far, we actually need to start filling in tactics move. Then we have to build in the code to actually move the player. And then we'll also fill in the tile class, because the tile class is going to contain all the information for the tiles that we're going to need for doing the graph theory, the BFS, the breadth first search. And later on, we're going to need it for the A star we're going to use for the NPC. So for starters, I want to set up the tiles with some public variables. So public bool current equals false. The tile is current if a player or NPC is standing on it. This is the player or PC who is actually going to do the movement. And we're going to do some color changing. So if, actually it's not in start, it's over update. If current, just get component renderer dot material dot color, and we're just going to set this material to color dot magenta. We're just going to set it to a little bit of a kind of pinkish color. The next one is public bool target, also false. Target is actually going to be where we're moving to. So this is what the player is going to select. That becomes our target. When the NPC decides where they're going to move, that'll become a target. And so we're going to add, at this point, get component renderer material color, and we're just going to make this one green. Now, how do we tell the player which tiles they can move to? We're going to do that by calling them selectables. Anything that's selectable, they'll be able to click on. And so our goal for the player is going to identify, using BFS, the breadth first search, identify what the selectable tiles are, and then when they click on it, then we'll move the player from their current position to the target position. But they have to click on the target position. And finally, if there is no flag, if there is no current target or selectable, then we are just going to set the color back to white. So white is the default color. If we actually go and play with that now, if I click on a tile and now it's compiled, I click on current, I'll have to play it first. Turns pink. If I click on target, it turns green. If I click on selectable, it turns red. We're going to use those visual cues. And these colors will work for textured tiles as well, because all we're really changing is the tinting not the texture. So, for example, I have a texture on these of this cube, which is just a white with a black border. It maintains that color even though we recolor it. We're going to need a lot more variables than this, but this is just our start. One of the other things that we're going to need is a list. And it's going to be a list of tiles. And it's called the adjacency list. When doing graph theory, we create an adjacency list or an adjacency matrix. In this case, we're going to make a list, not a matrix. A matrix is just a 2 by 2. In this case, we're going to use a list. And what we're going to do is identify the neighbors. The neighbors are the tiles next to the current tile. So this tile will have up to 4 neighbors. In fact, let's use an example right here. So currently I have tile 5 selected. This tile has a neighbor here, and the other neighbor is in front of the player. There's no diagonal movement inside of this game. We do not allow them to move diagonal. It is strictly, and this is standard for tile games, we don't want to put in, and tactics games too, we don't want to put in diagonal movement. If this were a non-tactics game and more of a real-time strategy game using a tile system, then we would allow diagonal movement. But we probably wouldn't be using the BFS algorithm, because the BFS algorithm doesn't really work for diagonals because it doesn't really use distances. A star, what we're going to use for NPC movement, that does really well with diagonals because we can use a cost function for identifying the fact that diagonals is actually the square root of 2, which is 1.44. It's actually longer to walk diagonal than it is to walk next to. However, walking diagonal is faster than going right than up. But for our purposes, we are not going to allow diagonals. So when we create the adjacency matrix, we need to take into account all the neighbors who are adjacent that are also passable. One of the other things that we want is the ability to determine if a tile is walkable. And in general, a tile is walkable. But there may become a time where we want unwalkable tiles. For example, deep water. Deep water is usually not passable by a normal unit. Flying units tend to be able to pass it, but I'm not going to cover flying units. That's a whole other ball game. But in general, units cannot walk on deep water, walk through deep water. So we're not going to cover that. So in general, all tiles will be walkable, but we can designate some tiles as unwalkable. For example, we don't want them walking on lava. That would be bad and quite painful. This is not actually counter tiles that have obstacles sitting on them, for example, rocks or trees. Yes, we could designate those as walkable, but we're also going to write an algorithm for determining if there's an obstacle sitting on top of a tile. For example, another player. You cannot step on opposing players. Now, most tactics games you can move through players on the same team. I'm not going to allow that movement either for now. It's actually easier to ignore that and assume if there's something on a tile, that tile will become unwalkable. However, we're not going to flip this flag. This flag is strictly for tiles that movement is impossible. And in general, I'm going to ignore it, but we want the ability to be there. And when we create our adjacency list, we're going to take into account the walkable and then determine if that tile is walkable or not. So for BFS, we're going to need a few other variables. Breadth first search. One is visited flag. A visited flag means bool, not void, means the tile has been processed. We only process a tile once with BFS. The other is the parent. We want to know who the parent tile is. The reason we want to know who the parent tile is that once we reach the target, we walk backwards to the parent of the target, to the parent of that parent, all the way back to the start tile, and then quickly allows us to identify who the tiles are that are actually walkable for us and how to get there. This is important to use when the player clicks on a tile. We then have to move from tile to tile until we reach the target, and so we actually have to define the path, and the parent will allow us to find the path. And you'll see when we get to that part in the code how we work backwards from the target through the parent to identify the path itself. So the last variable we need is actually distance. Now, distance isn't really part of BFS. What the distance is the distance is how far each tile is from the start tile. And the reason we're using it in this case is that players and NPCs can only move a certain amount. We talked about this already. Usually we're going to start with a value of 5. So the further away a tile is, the greater the distance is. At a certain point, we're going to hit that distance and we're going to stop, because we do not want to create selectable tiles that are outside of the player's range. That is how we're going to keep the player in the bounds of where they can move. So that distance, well, again, not part of BFS, that we're going to add to the BFS algorithm to prevent mapping the entire game world and make it selectable. We only want selectable tiles to be those within the distance of the player's capabilities. So one little helper function we're going to need is called reset. When we start, well, every frame we're going to have to, for every turn we're going to have to define everything over again. So we reset all the variables back, and we're going to use that void find neighbors. So every time we call the find neighbors function, we reset the tile back into the original state, and we also have to clear the adjacency list. So adjacency list dot clear will remove any adjacent, reset our flags, and then from here we can go and find the neighbors. Now to find the neighbors, we're going to check each individual tile to the right, to the left, up and down. Now, by saying up and down, I actually mean along the z-axis, not the y-axis. So we need a direction. So vector 3 direction. And so we call check tile, and it's going to be vector 3 dot forward, check tile vector 3 dot forward, but this one's going to be negative, so it's the negative 4, which was the opposite direction. Check tile vector 3 dot right, that's going to be in the z-axis, and then the negative right. So we check the 4 directions. Notice there's no up, because in general we don't really concern ourselves with up. We will actually jump onto tiles that are higher, which brings me to one more point. We are actually missing something here. The jump height. The jump height is essentially different, could be different for every player. It's how many tiles they can jump up or down. So a jump height of 2, which is going to be my default, the jump height of 2, if there's a distance of 2 between the current tile and the tile next to it, that is considered walkable. That's a neighbor. If it's greater than 2, or this unit can't jump that high, then it becomes unwalkable. So this allows us to define walls that are too tall to jump on. It also defines walls that are too low to jump, because the character would break a leg or something, however your fiction works. And so we use the jump height, which is different for every player. Some players, like ninja characters, have really high jump heights. Flying characters or characters with wings can also have expanded jump heights. And some characters, which are very unathletic, like wizards, or heavily armored characters, tend to have lower jump heights because they just don't have the athletic ability, or the armor they're wearing is too heavy. So they have a smaller jump height, which gives them a smaller range of motion. Typically, characters with smaller jump heights also have lower movement costs, but that's not always true. So we're going to use the jump height to help us determine if a tile is reachable for this particular character based on how high the tile next to it is. So to determine if there's a tile next to us, and if there's a tile even there, or if it's within range of our jumping, we're going to use physics. So physics.overlap box. Now physics.overlap box returns an array of colliders, because we can actually hit more than one object. Anything that has a collider on it could potentially be hit by this box. So we're going to filter it, so just look at tiles. The other thing is this half extents defines the box, but half the box in each direction. So we're going to have to calculate how big that is in a minute. First, let's fill in the center, which is transform.position plus the direction. That's going to determine the center of the box that we're going to use, which is an invisible box, to see if there is a tile next to us. So because every tile is 1 unit away, so it's position x5, this one is position x6, it is 1 unit away. So his position is 500. Then we use, this is actually, the orange arrow here means right. So direction of vector 3.right, go from 500, we'll actually make it 600. So we will actually check in the center of this box for a tile, which is exactly what we wanted to know if there's a tile there. Now we have to define the half extents. And for now, I'm just going to make a new vector 3. And I'm just going to pass the half extents, which I apparently misspelled. Twice. So that half extents is that half extents. Once we have that working, which I'm not done up there yet, but once we have all that working, we're going to iterate through all the colliders, which is called item in colliders. and then we'll process each collider. So let us calculate the half extents. We just need to check to see if there's a tile there. A tile is 1 by 1 by 1. So we want to know, we don't actually have to use a full 1. We can actually use like 0.25f, 5f, 0.25f. Now, the y, though, is incorrect because we actually have to compute the jump height to know if there's a tile that is reachable through jumping. So a tile is 1 high plus the jump height divided by 2. So if it was a jump height of 2, then we can go, because remember 1 divided by 2 is 0.5, which is half the size of our tile. And then we can jump up 2 or fall down 2. So that'll give us our range of jumping. And then, so the y will vary, but we'll always use the same x and z just to make sure we're inside the tile. Next up, determine if this is a tile. So tile equals item.getComponent tile. This will return the tile if there is a tile there. If it's not a tile, meaning it could be a player or an object, if there's no tile there, then it returns null. So if the answer is null, then it's not a tile, and therefore we don't care about it and we just let it go. The second thing we're looking for is that we only care about walkable tiles. If this tile isn't walkable, then we don't need to process it. Even though it's adjacent, it's not something we can walk on, and therefore we're not concerned about it. So ignoring non-tiles and ignoring non-walkable tiles, that's what we're going to do. So not equal to null means there is a tile, and walkable means that we can get there. And by the way, normally this would crash if tile was null, so we make sure that testing the null first, and only if it's not null will it actually test to make sure it's walkable. Now, at this point, we can say we found an adjacent tile. So adjacency list, add tile. Except we're not done. What about if there's something on top of the tile? Remember, we talked about tiles being blocked by characters. If there's something on top of this tile, it is not walkable. Even though it says it's walkable, we actually cannot walk on it. So we want to do a quick check, and we're going to use, again, physics to test to see if there's something there. Now, the first time we used physics overlap. This time we're going to use a raycast. And we want a raycast. It's going to have a hit variable. So if raycast, actually it's physics dot raycast, and it's going to be from the tile's position. So tile.transform position. It's going to be in the up direction, positive y. It's going to output the hit variable, and we're only looking for a distance of 1. Now this returns true if it hits something, and therefore we want to say not raycast hit. So now if it actually hits something, we're going to return true, and then this is false. So the only way we add it to adjacency list is if the raycast does not hit something, and returns false, then the not symbol turns to true, and therefore we've hit it. So really what this is doing is that from the center of the tile going up 1, which will put it at about 0.5 above the edge of the tile in the up direction, and it just looks to see if there's something there. If there's something there, don't add it. If there is nothing there, then we add it, and it becomes part of our adjacency list. So now that we've been able to calculate in all 4 tiles and determine if the tile is there and if it's reachable by the current player's height, and then there's nothing sitting on it, we've now defined the adjacency list. Once we define the adjacency list, we can now do breadth first search to determine selectable tiles. So I'll see you in the next video where we'll cover the BFS algorithm.